Welcome back to The Explainer. Today, we're uncovering the invisible math that is actively shaping the physical spaces all around us. From ancient temples to cutting-edge virtual reality, there are underlying geometries that literally dictate how we experience and feel inside a building. Okay, let's dive into this. Here's our roadmap for today. First, fractals in human architecture. Second, the base scale framework. Third, the line limit, total flattening. Fourth, the point limit, spatial collapse. And finally, the practical architectural threshold. I want to kick things off with this brilliant quote from Metropolis magazine. It goes, "The boundary of a room is perforated with smaller structures like rectangular doors and windows. These repetitive perforations at smaller scales will often continue on down to the scales of detail and ornament." What this tells us is pretty profound. A room's boundary isn't just a dead, static wall. It's a living, perforated fractal. And it turns out, our human brains intuitively find that kind of fractal setup incredibly intelligible, organized, and, honestly, beautiful. And this brilliantly illustrates exactly what we're talking about. What we're looking at is built entirely on nested scaling, structures within structures, perfectly echoing those natural fractal patterns. And this isn't just some abstract pie-in-the-sky theory. It's actively being built right now in virtual spaces to make them feel inherently more human and relatable. Section 1. Fractals in Human Architecture. To really grasp why this matters, we kind of need to look back historically. Think about Euclidean modernism, like Le Corbusier's minimalist, stripped-down boxes. Critics often call these dead spaces for a reason. Now, contrast that with fractal traditionalism. This represents the rich, self-organizing fractal networks of traditional environments. Think of the winding streets of Bruges or Edinburgh. Those spaces offer multi-scale interactions and massive synergetic, biophilic benefits. But historically, designers faced a huge challenge. How do you calculate and scale these complex fractal structures without relying on rigid, discrete geometric jumps that were just an absolute nightmare to actually build? Section 2. The Base Scale Framework. Well, to solve that historical challenge, we use something called the base scale decay rate. Think of this variable d as a unified parametric tuning dial. It completely controls the spatial envelope and the recursive decay rate of a structure. Without getting bogged down in the heavy algebra, you can literally imagine d as a physical slider on a soundboard. When an architect moves this slider, they are dynamically stretching or crushing the physical space of their building, all without any sudden disconnected jumps in the geometry. It's totally seamless. Now, what's really interesting about this slide is how incredibly elegant this math gets. By setting one side of the underlying geometry to 1, the architect can use just that single variable to dynamically dictate the spatial decay rate. You no longer have to painstakingly balance 3 independent sides of a Pythagorean triangle. No way! You just adjust that one single slider to control exactly how fast the space shrinks as it spirals inward. Let's put some familiar numbers to this abstract math to really anchor it. The silver ratio sits at roughly 0.414 on this dial, a number heavily used in classical surface designs like Japanese pagodas. And the famous golden ratio? That sits at roughly 0.618. In the past, architects were kind of trapped, having to jump discretely between these specific fixed metallic ratios. But with this new base scale dial, those famous ratios are literally just 2 stops on one continuous, smooth slider. But that raises a pretty massive question. What happens if we push this mathematical dial to its absolute physical limits? Like, what actually occurs when we sweep the slider away from those safe, classical ratios and push it all the way to the unbuildable extremes? Section 3. The line limit, total flattening. All right, welcome to the first physical dead zone, where pure math completely breaks down for actual physical buildings. We call this limit 1, and it happens when our decay rate d approaches 1. As d gets closer and closer to 1, the spatial decay effectively drops to 0. Those step increments in our recursive structure, they don't shrink anymore. Instead, the vertical height just shrinks down, and the entire geometry flattens out completely into a continuous, infinite trajectory. So mathematically, this means you have 0 area contraction. Now, that actually makes it theoretically perfect for something like an active, non-decaying photon in quantum electrodynamics, traveling on a linear path without losing its scale. But for architecture, it is a total physical dead zone. You absolutely cannot enclose a space or build a functioning room if your geometry has totally flattened into a one-dimensional line, right? Section 4. The point limit. spatial collapse. Let's move to the exact opposite extreme and see how this builds. We just looked at the flat line where d approaches 1, but what if d approaches 0? Here, you hit the point limit. The area vanishes instantly and a violent power loss spike, creating this infinite, deeply compressed stack. It's essentially a spatial black hole, mimicking a dense mass core. Again, totally fascinating math if you want to store hyperdense data, but an absolute nightmare if you're trying to design a livable, breathable room. The physical space just completely collapses in on itself.
Section 5. The practical architectural threshold.
Okay, let's step back from the edge of the mathematical abyss, shall we? Let's return to safe, buildable reality. Just take a look at this colorful spiral tessellation. It perfectly showcases a practical scaling factor sitting right there in the middle of our dial. This is exactly what a harmonious, gapless structural system looks like when you stay safely away from the total flattening of 1 and the violent spatial collapse of 0.
So the crucial point is that this 0.1 to 0.9 range isn't just some arbitrary geometric limitation. Not at all. It is a hard-won, physical Goldilocks zone that represents a highly practical architectural and fabrication threshold. By staying inside this 0.1 to 0.9 sweet spot, architects successfully avoid the physical dead zones of flattening at one end and spatial collapse at the other. It allows them to use the slider for arbitrary micro-tuning to precisely optimize acoustics and structural loads, all while maintaining completely gapless, overlap-free tessellations. It's absolutely essential for human adaptive fabrication.
Which leaves us with a profound question to end on today. How will mastering these mathematical thresholds reshape the self-organizing cities of our future? As we finally move beyond the rigid, dead boxes of the past, understanding this Goldilocks dial gives us the exact tools we need to seamlessly bridge the realm of pure math with our everyday built reality. Thank you so much for joining me on this explainer, and keep questioning the incredible geometries shaping the spaces around you.